This video is on satellites as part of P5. So there are two types of satellites that you basically need to know, which are polar and geostationary satellites. So the task that you have for this lesson is to do a visual graphic, which is to compare polar and geostationary satellites. So what you want to have is, between polar and geostationary satellites, you want to do sort of a mind map of all the similarities between them, and then sort of coming out from polar and geostationary satellites, you want to have all the differences. So a satellite is any object that has a trajectory, which is a circular orbit or an elliptical orbit around a larger body. So a satellite orbits a larger body. So for example, Earth is a natural satellite that orbits the Sun. The Moon is a natural satellite that orbits the Earth. Obviously there are natural satellites like planets or comets, but then there are also artificial satellites, which obviously we man-make and put up into orbit. So both polar and geostationary satellites are artificial, they're man-made. Now, satellites have to go a certain speed to stay in orbit. If they're too fast, they'll fly out of their orbit and drift off into outer space, and if they're too slow, then they would fall back down to Earth. So because the force due to gravity is stronger closer to the planet, satellites that are in low orbits, they have to move faster than the ones in higher orbits. And the satellites that are closer also have a much shorter period, and the period is the time taken for one complete orbit around the planet. So the difference between the two types of satellite is that a polar satellite orbits over the poles. It goes over the north and south pole. So because the Earth is rotating underneath it, it will travel its trajectory, the path that it takes, will travel over all of the Earth as the Earth rotates underneath it. And that's a polar orbit. A geostationary one is a satellite that orbits around the equator, and the orbital time has to be 24 hours. So the period is 24 hours, so it takes that long to go around the Earth once. And that means that as the Earth rotates underneath it, it stays over the same point on the ground. And that's why we call it geo, which means Earth or ground, and stationary, to stay still. So it's over the same point on the ground the entire duration of its orbit. And it must be over the equator. So, polar satellites then, a couple of other extra things. So polar orbits, they have to orbit usually over the poles, and they have very low orbits, so they're between 20 kilometers up to 100 kilometers. Their period can be as short as 90 minutes, so it doesn't take long for them to orbit the Earth once. So in a day, they'll typically go around the Earth maybe 14, 15, 16 times, depending on their actual velocity. As the Earth rotates underneath them, their trajectory will pass over a different point on the Earth with every passing orbit. So that means that their uses include things like weather forecasting, because they can take photographs of weather patterns over a large area. They're used for spying, for mapping the Earth's terrain, military uses. They're not very expensive because they're not very high up in orbit, so it's very easy to get a rocket to get them to that height. It's very and they can, when they're taking photographs of the Earth, they can give an awful lot more detail. So, you know, Google Maps will have been made using polar satellites. The signal strength is always a lot higher as well. So in terms of retrieving data, that's easier because they don't cover as much of the Earth's surface with their transmission capabilities, and so but the signal is much higher. Now, because they're in lower orbits, so they've got a lower orbital radius, that means that they first of all have a higher orbital speed. They're travelling faster. They have a shorter period, which we can see by the fact that it only takes 90 minutes for them to go around once. And both of those things have to be true because the gravitational force is so much stronger closer to the Earth, and therefore it has to go faster so that it doesn't fall back down to the Earth. Now you can see over a day how the trajectory of the polar satellite would vary over different points in the Earth. So you can see in the middle of the picture, the United Kingdom, that actually the satellite in a day maybe has only passed over the United Kingdom perhaps once in its flight path. Now a geostationary satellite, they have to orbit over the equator, and the period is exactly 24 hours, and that means that they stay over the same position. The uses of geostationary satellites are largely for communication. The reason for that is because you want to know where the satellite is in order to be able to transmit and send signals efficiently. Because they have a much higher orbital radius, it's all more in the region of 500 kilometers upwards above the Earth, then their orbital speed is a lot slower, which is necessary for them to have the longer period, and they experience a lower gravitational force because they're further away from the Earth. Now, the orbit has to be above the equator because obviously it's the equator is rotating around the Earth's axis of rotation. If you were to try and put an orbit north to south, because the Earth is rotating underneath you, you'd never be geostationary. You can also see on the little diagram the impossible orbit, which is an orbit that would be over some point that isn't the centre of the Earth. And you've got to remember that because the gravitational force acts always towards the centre of the Earth, if you had a satellite here at this point, then the gravitational force would be acting back towards the centre. And obviously for something to travel in a circle, like at this point here, the centripetal force has to act towards the centre of the axis of rotation. Now, if there was a force here, that would cause the satellite to veer off in this direction, and obviously it would be changing its position over the Earth constantly. So a geostationary satellite has to be over the equator, otherwise the centripetal force doesn't act towards the centre of mass, which is at the centre of the Earth. And this would be an impossible orbit. It also takes a lot more energy to get them to this height, so because they're much further away from the Earth, you have to put a lot more energy in, so they're more expensive, but they can cover a much larger area, so with the communications that's obviously an advantage. They do have to have higher power transmitters though in order to get the signals to and from the Earth, so the transmitter from the satellite can spread out over a large area. Okay, so you should be able to use that to do your comparison. Now what you need to do is to use all that information to summarise it, possibly go back, look at the parts of the video, freeze frame it, and then write down any notes that you need, and then have a go at answering the 6-mark question with all that information.